So here in lecture 11.9, we're going to complete our exploration of maze routing. And we're actually going to look at just a slightly different topic, but again, something based on the core maze routing method. So again, over and over, one of the things we've been emphasizing is that one of the things that's just great about the maze routing idea is that it is so flexible and so adaptable. All of the routers that we've been talking about so far in this lecture series are what are called detailed routers. And what a detailed router is a router that actually embeds a wire in a physical way that could make a physical path. There's another kind of a routing process, and these are called global routers. A global router does not put the physical wire down in the physical final path. The global router tells you, roughly speaking, the wire wants to go kinda sorta over here. Think of this as a hierarchical decomposition of routing. Instead of decomposing the chip surface into a gigantic grid of tiny little cells, each of which can fit one wire, we decompose the chip surface into a coarse grid of cells, each of which could hold, say, a couple of hundred wires. And on this coarse grid, we route. What does it mean to have a cost in this coarse grid? What does it mean to traverse a cell in this coarse grid? What does it mean to be an obstacle in a coarse grid that's the size of 200 wires on this dimension and 200 wires on this dimension? There's an entire parallel ecosystem of ideas in global routing that lets us coarsely and efficiently plan the macroscopic paths of the 25 or so million nets on a really big ASIC in an efficient way, so that when we finally invoke the detailed routing, we don't actually run the maze router on the full surface of the chip. We run it in little sort of boxes where we know the net already wants to go. And the beautiful thing is, it's just another maze router. It's just another expansion process. It's just another interesting set of cost functions. And it is really, really the way big things get routed. So let's finish our exploration of routing for ASICs and the maze routing method in particular by talking about global routing. We're going to finish our discussion of maze routing by kind of popping up a level to sort of talk about the big picture problem again. And as a starting point, we're going to do a little bit of a reality check. Here's just my great big giant chip that I showed at the beginning of this lecture. This is an industrial, actually a processor chip. Let's say that something like this is maybe 1 centimeter on a side, 20 to 50 million nets. And in a modern integrated circuit technology, the grid, as we taught you about the wiring grid, probably has the pitch for the wires, which means the center of one wire to the center of the closest adjacent wire, which you can think of as just the size of a grid cell, maybe about 100 nanometers. So if you have 1 centimeter and you have a 100 nanometer grid, you have 100,000 grids on each, on the x-axis and the y-axis. And then if you multiply that by 10 different routing layers, you get about 100 billion grid cells. So this is one of the reasons I said we care about how big the grid cells are, and we'd like to have as few bits as possible. But do we really just do it like this? And the answer is not really. There's some more interesting stuff that happens. So the first fact, just as an aside, is that in real industrial ASIC routers, where you have like 10 layers of wiring, every other layer of metal wiring has a preferred direction. So let's say, for example, metals 3, 5, 7, and 9 are vertical, metals 4, 6, 8, and 10 are horizontal. And this is how strong this preference is just a function of the router and the preference of the user. But I'm just going to show you an example where it's strictly enforced. So suppose I have a chip and I've got a pin on layer 3, as I've shown over here, and I've got a pin on layer 6. How do I route it? The typical way I'd route something like this is I'd route it vertically on layer 3, and then I'd pop a via in, and then I'd go horizontally on layer 4, and I'd pop a via in, and then I'd go vertically on layer 6, and I'd pop a via up to vertically on layer 5, and I'd pop a via up, and I'd drop that connection in on layer 6. And so the idea is that if you need to bend, use a via. And people will play games with the bend penalty, you're allowed to bend, but boy, very, very little. And the whole idea is that the wires on these layers look like mostly straight lines. right? Which makes it much, much, much easier to route a lot of things that are just going in straight lines. It's harder to block stuff. Okay? And when you need to go around, you go to another layer that's mostly straight lines. So that's one of the ways you deal with this complexity. But there's another interesting way, which is that there's a divide and conquer scheme. So how do you deal with the huge scale of chips? The first kind of routing you do is actually something called global routing. And global routing is, again, a grid-based maze routing kind of a thing. And so we have a grid on which we run a certain kind of a maze router. But the thing that's different is that the grid is not a one wire per cell grid. The grid is now very coarse. So the grid might be a set of boxes on the surface of the chip that are maybe 200 wires by 200 wires in size. So the grid is extremely coarse. And the big idea is that you run the maze router on your wire just through these great big coarse regions. So I've got a little yellow wire here going from a pin in the upper left to a pin in the lower right. Now, why am I doing this? So here's the basic idea. I'm going to chop the chip up into these coarse regions. Later on in the flow, I'm going to use a real router to put the real wires in. All of the routing that we've actually talked about so far has a name. It's called detailed routing. And why it's called detailed routing is that it plans the exact final path of the wire. Now, in this kind of routing, we are not planning the exact final path of the wire. We're just telling you roughly where the wire wants to go. And what roughly means is through this set of big coarse grids. Those things have a name. They're often called G-boxes. Okay, so that's a G-box. A G-box is a grid in a global router whose size is perhaps 100 wires by 100 wires, 200 wires by 200 wires, could even be bigger. And the idea is we're just going to do a sort of a large-scale plan for where the wires want to go. So what global routing does is it makes sure that the overall wiring congestion is reasonable. And the way you can think of that is that it balances the supply of how much space is available versus the demand of how many paths want to go here. And so the other way to think about it is that global routing generates regions of confinement, a coarse path for a wire. So I route the wire in the G-box grid, and what it tells me after I've routed the wire is that when I am ready to embed the wire in detail, I should put the wire in the yellow box, the yellow serpentine path, the thing with the star in it. And you know what? That's going to be tremendously helpful to the efficiency of the router, because if I don't have to expand the route across the entire surface of the chip, if the region on which I run my detailed router is just the smaller yellow box, it's going to be dramatically faster. So what detailed routing does, what the kind of routing we've been teaching up till this point does, is it embeds the exact paths in these regions. And the simplest model is a grid, right? You require the wires and the pins to use the tracks on this grid. So the global router in the picture on the left tells us to search for detailed paths just in the highlighted yellow set of G-boxes. And I'm showing you the sort of the individual routing grids on the inside, okay, to just give you some sense of, the fact that there's a detailed routing problem yet to happen. The detailed router on the right tells us the exact final path in this region by routing the wire on the grids inside. This means that you can balance the demand for wiring across the surface of the chip by roughly planning where the wires go first. It also makes the detailed embedding of the wire with your router much faster because you just don't have to search so much space. So what's really different about a global router other than that it is a very coarse kind of a routing grid? And the big answer is the cost function. Right, so in a detailed router, the grid cells are either blocked, which means they have a cost that's effectively infinity, you're not allowed to use them, or they have a cost proportional to how much you want to avoid them. In a global router, the cells have a dynamic cost. The way to think about it is that in a global router, the cells have memory. They remember
how many wires went through them previously. And so in a global router, the cells have a cost proportional to how many previously routed wires use this cell and how many more can fit in later. So suppose in my little example shown at the right of a little G-box, the G-box is 10 tracks. And we're just talking about, we're pretending there's just one layer to be very simple-minded here. So what does the G-box cost look like? Well, the horizontal axis says how many wires have been routed here. Okay, and the way a G-box, a very simple G-box might have a cost is that, out to maybe, 5 wires going through the G-box, the cost is low. It's whatever the appropriate version of 1 is in this router. But as soon as you start putting more wires through, it starts to get more expensive. And the idea is, I don't want to allow the router to try to put more wires in here than can fit in here. And one of the things that's going to happen is that, by the time you actually have 10 routers in here, what's going to happen is that you actually have something like infinite cost. Or you have, if it's not infinite, it's actually big. And you're going to highly discourage future paths from using this cell because it's all used up. You've had enough wires going into it that there's just no more space. And as you can probably imagine, you could be very, very sophisticated in your mechanisms for figuring out the cost of a G-box. For example, you could look at the sort of logic gates that are on the bottom in the G-box and say, well, do they already have a lot of wire inside of them? And you could look at things like other blockages. You could look at things like how many layers of routing is there? You could look at things like, does the wire that goes in bend? And does it put a via in? Because if you put a via in, you might actually need a little extra space depending on the nanometer rules. There are entire groups of people in real companies that spend their lives figuring out the costs for the G-boxes in global routers so that you do a good job of balancing the demand for wiring with the supply of wiring. And if you do global routing well, it makes the detailed routing so much faster and so much more efficient and so much more likely to succeed in routing all the nets. So, and it's cool for us because it's just another maze router with a cost function that has memory in it that remembers how many wires have already used a piece of the space on the chip surface. So, very cool. And so we come to the end of a very long, but I hope interesting lecture. This maze routing idea has been around a long, long time. I mean, people were doing, mazes, routing through mazes in the 50s, the first, routers for printed circuit boards in the very, very early 1960s. It's a very flexible cost-based search, and it can be recast to attack many different problems. That's one of the reasons people like it, and really, it really does dominate most modern routers. There are some big chip-level routers that use fancy dynamic grids because the nanometer rules are complicated. There are also some rather sophisticated gridless representations of space, but you still end up with something that has a best cost Dijkstra-like minimum cost path algorithm. You just get a much more sophisticated representation of space where, for example, if you want to sort of expand the path in a particular direction, you sort of dynamically build a model of what's out there, and then you search on it, and then you throw it away. There are lots of ancillary problems and solutions. You still route nets one at a time. Early nets block later nets. There are all kinds of tricks for that. There are a lot of iterative improvement strategies. You often route the nets multiple times. An interesting strategy is that you route every net as though all the other nets didn't matter. You just route them. Okay? And then you use the places where there are lots and lots of nets, too many nets, an unphysical amount of nets, and you use that to change the cost of the grid to make nets not want to use that space. You use the basically a demand routing to create a demand map, and then you use that to sort of put costs down, and then you can use that to sort of route things later. There are negotiation schemes where nets sort of route each other and rip each other up. One of the things you can do is you can route a net, and in the consequence of routing it, you can decide to remove a piece of another net and ask the other net to reroute itself. There's very interesting stuff there. There's a lot more hierarchy and abstraction going on in real routing. You absolutely do global routing for a big chip. You absolutely do detailed routing for a big chip, probably with something like a grid or some fancy dynamic data structure. There are a whole bunch of steps in real routing where you go in and you look at the actual rectangles on the paths, and you have to go in and fix all of these horrible nanometer scale physics rules. That's the sort of thing that's keeping everyone awake at night today. A lot of interesting computational geometry in those algorithms. But if you're going to know one thing about routing, know about maze routing and all of the interesting things surrounding it. And so that is our exploration of routing.